Okay, so we're here to think about surds and trigonometry, and as of last week, this is what I want to do. I want to share some ideas that if I had a year 11 at the moment, which I don't, because where I'm teaching is King's Math School only has year 12s and year 13s. But if I had a year 11, this is exactly what I would be doing with them, the sort of thing that I'd be doing. And all these questions have been taken from lessons I've taught, example sheets I've created, resources I've used with year 11s in the past. So I hope you like them. I hope they interest you, I hope they inspire you, and I hope to some extent they infuse your students, when you share them with your students. Possibly you're not being able to do so yet, but hopefully in the future you'll have an opportunity to do so. And then if you do get a response, it'd be lovely to know what it is. If you do share some of these ideas with your students, and you can come back and tell us, that went really well, or that was a total disaster, that'd be really great to know. So I'm hoping that you are able to cascade some of these ideas, maybe to your colleagues as well, and get some feedback from them. And as I always say, look, I've been teaching for over 20 years now, so I'm like a magpie. I definitely take ideas from lots of other people, and probably all the good ideas came from somebody else, and all the bad ideas came from me. So when we're thinking about teaching sort of the top set, the highest attainers, this is what I have in mind. Now, as I said last week, I have this in mind when I'm teaching every class. I have this in mind when I'm teaching every set. But actually, for a reason I'll explain in a moment, I think it's even more significant when you're teaching higher attainers. So in my teaching, what I'm trying to do is get across factual knowledge, procedural fluency, conceptual understanding, and making sure the students have these at their fingertips. They are accessible, and when they use them, they do so reliably, successfully, confidently, securely, and flexibly. If you want to put it in sort of student language, we're talking about I know that, I know how, I know why, and I know when. I know that the angles in a triangle at 180. I know how to work out the missing angle in my isosceles triangle. I know why the angles in a pentagon add up to 540. And I know when I'm given a question about tessellations, about tiles, which doesn't mention angles at all, I know when to use my knowledge of angles to answer a question about tessellations, even though apparently it's about tiling, it's about shape and measurement and fitting. It doesn't say anything in the question about using angles. So that's what I mean by that kind of accessible, reliable, confident drawing on knowledge about angles in a triangle, what they're up to, about using that to answer a problem-solving question, about adapting that with justification to a new context, pentagons, and then applying it in a particular context. And what I find with higher attainers is I often find they've got lots and lots of that. They've got loads of procedural fluency, but that is often lacking. So they just sort of go, well, it is. I know. I've done. I worked it out and I got the answer. But why? And often you get in top sets kids who've got basically really good working memories, and they remember what they've been taught, and they remember how to apply it, but they don't really understand what is going on. They don't understand the mathematics behind it. They don't understand the structure behind it. They can do the sums, they can do the questions, and they do well in tests, and they end up in the top set, but they haven't got that depth of understanding. And I come across that quite often. And that's why it's very much in my mind when I'm teaching these highest attainers. Though I sort of say that's what's in my mind, it's completely consistent with the national curriculum. So the national curriculum says that all students must become fluent, and sort of defining fluency like that. I think that phrase about varied and frequent practice is especially important. I think that phrase, varied and frequent practice, is really important. And that's sometimes what textbooks don't do. They don't give that varied practice. They must all solve problems. And again, you've got the same idea, routine and non-routine problems. And again, I look at a textbook and I often see lots of routine problems, but I don't see enough non-routine problems. And they must reason mathematics. So this is all taken verbatim from the national curriculum. And so again, developing an argument just using mathematical language. That how many times have your students said to you, yeah, I can do it, but I can't explain why. I know it, but I can't explain why. Or I can do it, don't know why. And so then developing that language, developing that precision about how to express themselves, how to explain themselves. So that's very much what's in my mind, developing fluency, solving problems, reasoning mathematically, so that they get that factual knowledge, that procedural fluency, and that conceptual understanding. How do we go about doing that? As we talked about last week, getting the maths from them. So think about Surds trigonometry, think about how to get the maths from them, Surds and trigonometry. These are the areas I thought about. So the fact that Surds are numbers, well, so what? Combining Surds, using Surds in geometrical circumstances, not just trigonometry, okay? Using Surds in algebraic circumstances, intriguing, and then using Surds in trigonometry. That's kind of obvious up to a point because of the special values, you know, sine 30 being half, sine 60 being root 3 over 2. So you can see where the surds come from in trigonometry, but we can do some rather nice activities which will test their application of those numbers, not just their recall of those numbers. But let's sort of start with the beginning. So I sort of say to my top set, what do we mean by root 2? And this would go, it's like 1.4. Or I did it on my calculator. So it's a number, okay? So it's definitely it's a number. It's a real number. It's on the number line. It's a real number on the number line between 1 and 2, and we can verify that because 1 squared is 1 and 2 squared is 4. So we're using the squaring property. So what is this property? So it has the property that whenever you see root 2 squared, you can rewrite it as 2. So root 2 squared has to equal 2, not sort of does equal 2, not happens to equal 2, but must equal 2, has got to equal 2. And that's a very powerful idea, that the definition of this number is that when I square it, I will automatically, without thinking, get the answer 2. Now, the fact that it's a real number is important. The fact that it's a real number tells me that it behaves like all real numbers do in arithmetic. So the things that happen in arithmetic, like, for example, that addition is commutative or multiplication is commutative, those results that we know from arithmetic, they will apply in these circumstances as well. Anything we do with arithmetic involving root 2 those properties of arithmetic will carry through, those axioms will carry through because it is a real number. So something like this, what I want my students to say is, well, it's obviously 2, it has to be 2, it's 2 by definition. What I often see is that, oh, well, you can use the rule, can't you? So it's root 2 multiplied by root 2, so it's root of 2 times 2, so it's root of 4, so it's 2. And they can go all around the houses to get the answer 2. Now, that to me is a really good example of fluency but not understanding. They've got fluency, they know the rules of surds, but they don't seem to have the most basic understanding that when you write root 2 and you square it, you get the answer 2. They don't seem to understand the definition of root 2. This is true by definition. It's not true by calculation. It's true by definition. And therefore, similarly, if I do root to the power 4, I've got root 2 multiplied by root 2 multiplied by root 2 multiplied by root 2. And again, what I often see is, well, look, that's root of 2 times 2 times 2 times 2, which is root of 16, which is 4, which is true, but that's not what I want. What I want to say is, oh, look, what you've got there is root 2 squared. What you've got there is root 2 squared. And so by definition, I've got 2 and I've got 2. And so by necessity, I've got the answer 4. So again, it's the same idea that these are equal by definition, not by calculation, but by definition. But also note what we have done, which is we've been playing around with the order in which we're calculating. So what I wrote initially was that. And the next thing I did was effectively put some brackets in. And then I said, well, okay, first of all, I'm going to work out the first product, the product of the first 2. Then I'm going to work out the product of the last 2. And then I'm going to work out the product of those 2 together. So I'm changing the priority of the products. I'm not changing the order of the factors. I haven't switched the root 2's around. Obviously, you can't tell, but I haven't switched the root 2's around. What I'm doing is I'm changing the priority of multiplications. I'm making that one first, that one second, and then that one third, rather than say the other way around. Now, am I allowed to do that? Yes, I am, because multiplication is associative. So multiplication is associative. And that property of multiplication, and that word associated with it, pun fully intended, the word associated is associative, that property of multiplication is something which students need to know, need to understand and be aware of And often they don't. They know what to do. They know that they can do this, but they don't have the justification. They don't know why that's the case. I've just realized, sorry, I'm hiding. Oops, sorry. So the chat is obscuring what I'm writing. So sorry about that, folks. So multiplication is associative. Right, then similarly with the next one, I've got 3 multiplied by root 2 multiplied by 3 multiplied by root 2. Now what do I want to do? Well, now I want to use commutativity because I want to change the order. I want to write this as 3 times 3 times root 2 times root 2. So I can do that because multiplication is always commutative. And then I want to put the brackets in. So I'm going to then invoke again associativity and say that this gives me 9 by 2 multiplied by 2 by definition. So therefore that gives me 18. And again, we've got the same result, that is equal, root 2 times root 2 is equal to 2 by definition, because root 2 squared is equal to 2. So I've changed the order of the factors by commutativity, and I've changed the priority of the multiplications by associativity. And I'm entitled to do that, but do your students realize that's what they're doing? And my experience is that no, they tend not to. And something like this, well, I mean, kind of obviously that's 2 root 2, and obviously that's 5 root 2. But why? Well, because root 2 is a real number. And by definition, if you add the same number 5 times, if you do repeated addition with the same number 5 times, that's what's meant by, or that is an interpretation of what's meant by multiplied by 5. So, so 3 plus 3 plus 3 plus 3 plus 3 is a way of saying what we mean as 5 times 3, or another way of saying that is 5 times 3. So root 2 plus root 2 plus root 2 plus root 2 plus root 2, another way of saying that is 5 times root 2. So repeated addition with the same addend is what, or can be rewritten as, multiplication. It's not the only way of interpreting multiplication. It's not the only way of interpreting multiplication. It's a way of interpreting multiplication. And then what about these 3 down here? Well, what I've got a negative factor. I have got the product of a negative and a positive, or a positive and a negative, or a negative and a negative. And so again, by the axioms, we know that, well, whatever the answer is, the first one is a negative number, the second one is a negative number, and the third one is a positive number, because root 2 is a real number, and it therefore behaves the rule that, behaves the axiom, or conforms to the axiom, that a negative number multiplied by a negative number gives a positive answer, and a positive number multiplied by a negative number gives a negative answer. I'm slightly regretting my use of the word axiom there. If you're wincing, you're right to be. Obviously, the fact that a negative times a negative gives a positive answer is a consequence of the definitions of arithmetic. It's not actually an axiom. So sorry about that, folks. So we know the first one is negative, the second one is negative, and the third one is positive. What actually is the value? Well, look, we've got root 2 squared. We've got root 2 squared. We've got root 2 squared. So the value is always 2. The sign of it comes from our knowledge about, if you multiply 2 negative real numbers, you get a positive product. If you multiply a positive and a negative real number, you get a negative product. So it's coming back to this idea again and again, that it is a real number. So arithmetic behaves like it should. And then coupled with the fact that whenever you see a root 2 multiplied by itself, root 2 squared, you know the answer is 2 automatically. And then we can do things like this. So what have we got here? We've got a number added on to its negative. So surely it's 0 by definition, because if you have any number and you add on its negative, you definitely get 0. That's what we mean by the negative. The negative is the inverse. It's the additive inverse. It's what you add on to get 0. And similarly, and what about here? Well, here we've got subtracting a negative, and we know that subtracting a negative is the same operation as addition. And similarly here, perhaps you might say we've got adding a negative, and we know that adding a negative is the same operation as subtraction. So adding a negative is the same as subtraction. Subtracting a negative is the same operation as addition. What about these two? Well, we're dividing a number by itself. So obviously the answer is 1. Or we're multiplying a number by its reciprocal. So obviously the answer is 1. You don't want the students to be writing, oh, look, it's root 2 over 1 times by 1 over root 2. So it's root 2 over root 2. So it's 1. We're multiplying a number by its reciprocal, and when you multiply a number by its reciprocal, you get the answer 1. That's what's meant by the reciprocal. Is it always true? Always, sometimes, never? Is it always true that if you divide a number by itself, you get the answer 1? If you multiply a number by its reciprocal, you get the answer 1? Well, what about if the number in question is 0? So it's really good to get students to think of generalizations and then to think, do those generalizations actually work? Are those generalizations actually correct? So we have kind of 4 calculations here, and obviously you can sort of see what I've done. I've kept the terms pretty much the same. But I have changed the operation. Those two, I sort of like those two. I'm going to ask my favorite question: what's the same? What's different? So you've got this sort of variation. You've got this procedural variation as they work through the questions. We're changing what they're doing from addition to multiplication, subtraction to division. And then what's the same? What's different? So they might well say, well, look, the second one's got a 3 root 2 rather than 2 root 2. That's fine. They can say that. That's fine by me. What else? If you think about the answers to those, what else might the students draw out as being the same or being different? I have to say out loud or put some ideas in the chat. What if you look at the answers to those? What do you think your year 11s might notice? Yeah, I mean, Amy, that's what I was thinking about. This sort of, yes, yeah, exactly. They'll say sort of something like the roots disappear. Yes. So I'd want them to sort of say, oh look, that has got answer 4 root 2, and that's got answer 2, and where's the root 2 gone in the second one? So I want to really think about, and then of course to articulate, well, so why is that the case? And so exactly as someone's put in the chat, when you multiply and divide, the roots disappear. So why is that? And of course, would that be true if we look at that example? If that was 6 root 2 multiplied by 2 root 3, would the roots then disappear? So we wanted them to, you want them to make statements like that, so that then you can then challenge it and go, well, was that always true? And then obviously move on to expanding brackets. So why do we do these in the same way as we work algebraically? Well, because we're using the fact now that multiplication is distributive over addition. And so when we have something like this, we can write it as 2 lots of 2 plus root 2, take away root 2 lots of 2 plus root 2, and then we distribute the multiplication over the addition. So we get 2 lots of 2, 2 lots of root 2, root 2 lots of 2, and root 2 lots of root 2. And again, you can see we can get the root 2 times the root 2 all squared happening again. I always like this one because and ones like it, because you get the answer 1. And you go, I thought 1 didn't have any factors apart from 1 in itself. I think they quite like the idea of factorizing a number. They like the idea of factorizing a number, which they thought they couldn't factorize. It's quite fun also actually do things like sort of 3 take away root 2 and 3 plus root 2 and get the answer 7. They go, but 7's prime. I thought 7 was prime. I thought prime numbers only had 1 and 7 as their factors. So again, to realize that, well, it depends what you count as a factor. It depends what you allow to be a factor. 1 and 7 are the only whole number integer factors. Or sorry, and there's also -1 and -7, of course. So positive -1, positive -7 are the only integer factors of 7. It doesn't mean there aren't other numbers that multiply to make 7, e.g. these 2 numbers. I quite like this activity. So get them to work out the first one, so it's going to be 4, and so it's going to be 6 take away 4 root 2, and then see how they do the next one. And actually, obviously what you want to do is again square it. You want to just go straight away. If I just square that, I am going to get 36 plus 32, so I'm going to get 68 take away 48 root 2. That's what you want them to do, but actually, I think what you'll find quite a lot of them do is that they'll multiply by 2 take over root 2 and then multiply again by 2 take away root 2. They'll go through it sort of 1 power at a time. They'll turn it into cube and then they'll turn it into power 4. And so then there's a question, well, what do you do there? I'm going to have to work out power 5, power 6, power 7 before I work out power 8. No, I can do the same thing in squaring. And then what's going to happen there? Well, hopefully they might start to see this idea of repeated squaring. So I can rewrite this as to the power 16, but then not to the 8, because that will give me 24 in total. So power 4, power 2, power 1. And then I can just use my answers. So I know what that is. I know what that is. If I square and square again, I will know what that is to subtract root 2 to the power 16. Obviously, these are going to be really big numbers. I'm not suggesting necessarily we do it practically, but getting them to think through the structure of it. So square, 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 and square. So that will take me up to power 20, power 16, and then I can go back and combine or multiply power 16, power 4, power 2, power 1, and that will give me a total power of 23. So I don't have to do 23 multiplications. I don't have to multiply power 1, power 2, power 3, power 4, power 5. I can do 1 squaring, so 1 multiplication, 2 multiplications, 3 and 4 multiplications to get up to power 16, and then combine them together with maybe another 4 multiplications. So basically I can do about 8 multiplications, not 23. So it's much, much more efficient. If you just build up 1 power at a time, squared, cubed, 4, 5, 6, 7, 23, that's basically 23 multiplications. If instead you use this repeated squaring strategy, you use far, far fewer, even though at the end you have to multiply them all together, but you're multiplying a much smaller number together at the end. What's this connecting with? Well, of course, it's connecting with binary. So you can think of this as being in binary because I've got a 16, no 8s, a 4, a 2, and a 1 to add up to 23 in denary, in base 10. So you're thinking of the power in binary and thinking, right, which binary powers do I need? I need a power 16, a power 4, power 2, and a power 1. And because a binary has the structure of doubling, to work out the powers, you just square it. If you square an expression with the power, then effectively you double the power. So that's quite a nice activity to get them to think through and give them a reason why something like binary might actually be interesting, might be relevant to them. So rationalize the denominator, make sure they can tell you what is going on. I see far too much of, well, yeah, you're multiplying by root 2. No, you're not multiplying by root 2. You're multiplying by 1. You're multiplying by 1 in the cunning form of root 2. You're multiplying by 1 as a disguised as root 2 over root 2. If you don't multiply by 1, you're going to change the value of the fraction. So you've got to multiply by 1, but it's 1 in a cunning form. It's the 1 disguised as root 2 over root 2. And I don't hear enough of that when I'm working with higher attaining students. They just go, yeah, multiply by root 2. Multiply what by root 2? The fraction. No. You multiply the denominator and the numerator by root 2. So effectively, you've multiplied the fraction by, and getting that 1 is well worth drawing out. It can be quite painful at times. And then similarly, kind of 4 over root 8. And then something like this, or indeed both of these two, I want them to stop and think. And obviously they could rationalize the denominator of each of them and sort of say it's 5 root 18 over 18, take away 3 root 72 over 72. So they could do that. But then there's a whole issue about lowest common multiples to find the common denominator. What I want to do is stop and think. Now, actually, hang on. What we've got here is 5. I was like, my pen seems to ground to a halt. There we are. It's 5 over 3 root 2. Take away 3 over 6 root 2. Oh, right. So the common denominator is 6 root 2. So that's my common denominator. So I can rewrite this as 10 over 6 root 2. Subtract 3 over 6 root 2, etc. and go from there. So recognizing that they should always be looking to simplify before trying to, in this case, rationalize the denominator. And if they want to rationalize the denominator, they certainly should do it with 3 root 2 and rationalize it by multiplying numerator and denominator by root 2. So multiply numerator and denominator by root 2, not by root 18. You want to multiply by the simplest thing that gives you a nice answer. And then once they've got that kind of idea across that what they're trying to do is multiply the denominator by something which makes the new denominator the denominator of the product nice in some sense, nicer than the one we started off with. And something like that is a really nice sequence of activities for them to work through. I'm not going to go through these and tell them what to do. I'm going to say, well, you tell me, you try something, what do you think might work and why do you think it works? So, you want them to be thinking, well, look, actually, if I have 3 plus root 2 and 3 take away root 2, then they might remember the difference of 2 squares and they might just have to work it out. Then by doing that, I get the answer 7, and 7 is nice. And so that's what I'm going to do. So what am I going to do here? What am I going to do here? And then that's a lovely little challenge. What am I going to do here? What's the point about this question? What's the same? What's different? Well, again, let's take a step back and simplify first. So this isn't multiply numerator and denominator by 72, root 72 plus root 2. That's not what we need to do here. We need to say this is 40 over 5 root 2, because it's 6 root 2, take away 1 root 2, so it's 5 root 2. Oh, look, that cancels, it's going to be 8. And so therefore, now when I multiply numerator and denominator by the nice easy number root 2 over root 2, I get 8 root 2 over 2, which is 4 root 2. So yes, they want a method to multiply numerator and denominator by it's called the conjugate, which is a word worth sharing with them. So those two are what are called conjugate surds. And so you multiply numerator and denominator by the conjugate, but not always. The first thing you do is you check to simplify. You do not want to multiply by root 72 plus root 2 for that fourth one. We want to simplify first. And then there's a question of what does the conjugate look like in this case? Is it 1 take away root 3 take away root 2? Well, let's find out. Let's multiply numerator and denominator by 1 take away root 3 and take away root 2 and see what happens. Just see what happens. And having done all of that for root 2, having spent a good couple of lessons doing that for root 2, I then go back and do the same for root 3 and get me really think about what is happening with root 3. Well, root 3 is a real number, so it has all the arithmetic properties, commutativity, associativity, and distributivity. Multiply by root 3 is distributive over addition, and that whenever I see a root 3 squared, without even thinking, I replace it with 3. And at some point, I will say to them, when you're doing further maths in the sixth form, I'm a big fan of that phrase, when you are doing further maths in the sixth form, you will meet the number j, and j has the property that j squared equals -1. So here, whenever you see root 3 squared, you replace it with 3. In sixth form further maths, whenever you see a j squared, you replace it with a -1. Without even thinking about it, you replace it with a -1. So questions like this, is this true, or are they true? Is either of those true? Is either of those true? Is either of those true? So not give the question, simplify this, but ask the question, has this been simplified correctly? Is this true? Apologies. Sorry about that. And then how would they go about? How would they go about showing it? Well, there are a number of ways, but an appropriately formal way for the higher attainers to be demonstrating is something like the following. So let's take the left-hand side and square it. So I've got 5 times root 2 squared, which is 5 times root 2 times by 5 times by root 2, which is 25 times 2, which is 50. So what? Well, it's supposed to be 10. Why is it supposed to be 10? It's supposed to be 10 because I'm claiming this is the same as the square root of 10. And what's the one thing we know about the square root of 10? It's a number which, when you square it, gives you 10. By the way, notice I'm trying to be careful and say a number, which when you square it gives you 10, not the number, which when you square it gives you 10. Because if I say the number, I'm assuming there's only one, and that's not true. There's a negative square root of 10. But also, even forgetting that, if I say the cube root of 2, then how do I know there aren't any others? I don't. So at least not without thinking quite hard about it and know the real solution. Sorry. So I would always be careful and say a cube root of 2 or a square root of 10 to emphasize that this number has the property. It doesn't mean that other numbers don't also have the property. So I'm claiming here that 5 root 2 is the same as root 10. That means when I square 5 root 2, when I square the left-hand side, I'm supposed to get the same as squaring the right-hand side, which is 10, but I don't. I get 50, and therefore that claim can't be true. But that logical deduction, I should get this, but I don't. I get this instead. Therefore, the original claim can't be true. Is quite sophisticated and therefore well worth doing with your higher attainers. Make sure they can explain the reasoning behind the fact that what they probably recognise as not being a true statement. And obviously, then similarly for this one, you might have to have 5 root 2 multiplied by 5 root 2 in brackets, expand the brackets, and see what happens. Whereas, say, one of these is correct and the other one's not. Well, let's do the correct one. Okay, so same idea. Let's take root 3 times by root 2 and square it. So that gives me root 3 times by root 2 times by root 3 times by root 2. And then using my commutativity, that's going to be 3. And then using my sensitivity, so first of all work out the root 3 times root 2, then work out the root 2 times root 2. I get 3 times 2, which is 6. So what? Well, that's good news. That's good news, because at the beginning I said that this product could also be called root 6. And if I call it root 6, I'm saying that when I square it, I get 6. Root 6 is the ink on paper. It's the pixels on screen, which says, here is a number which has the property that when you square it, you get 6. So I'm saying the left-hand side has that property, and it does have that property. So all is well, all is good. There's a slight wrinkle here about being careful about positives and negatives. You know, how do I know that these actually aren't positives and negatives? Because obviously they would square to give, but the negative square root of 6 would also square to give the same answer as the positive square root of 6. So I just have to say, look, this symbol, this root symbol means the positive square root, so we can assume that everything is positive. But it's a good student who raises that. It's a good student who says, well, hang on, surely some of these numbers can be positive, some of these numbers can be negative, and you'd still get the same answer when you squared them. So be on the listen out for that. And then what I would do is say, look, you've seen some claims. You've seen some claims about it being root 10, root 7, root 6, root 5. Maybe one of those is true. What about the other one? So then I say, make it your own claims. So make it your own claims involving root 2. One should be true, but far from obvious, it's quite subtle, and one should be false, and then swap and share. So that idea of, so if you go back to the slide about getting the maths from them, one of the things I said was make up your own, answer each other's, or give me another reason, give me another example, give me another diagram, another method. So I hope the last few slides I was talking about a moment ago, that seemed to have mislaid. Where did I put them? There, yeah. Yeah, that's very much make up your own claim, make up your own examples, make up your own things which you think are true. So I hope you can see how that is a way of exemplifying what we talked about at the beginning. Similarly, this. So are these always, sometimes, or never true? Again, there's that prompt, always, sometimes, never. As they work these out, think what great fluency they would be developing. So, you know, as they tested whether, say, root 3 times root 5 is root 8, and root 3 times root 5 is root 15, etc. As they tested those in the way that we've been talking about, by doing an appropriate sort of formal argument, as a mathematically watertight argument, if you really, they get all that fluency practice, but then also they'll be generalizing to make those bolder predictions, those broader assertions about the combination, about operations acting on the surds. And you know, obviously there's some sort of special cases here. So these two work quite well if B is 0. So in fact, even those 3 work quite well if B is 0. That's a bit of a nightmare if B turns out to be 0. That's obviously a bit of a problem, that one. So thinking about, so are there special cases? A lot of them also say straight away, no, it's not true. They won't think of 0. They don't think of 0 as being nothing at all, rather than being the number equally spaced between 1 and -1, and therefore on the number line, and therefore has all the properties that numbers have. So, you know, simplifying surds is an important topic. It's an important topic for fluency. You know, you want them to know that root 50 is 5 root 2, whereas root 20 is 2 root 5. But how to practice it, yes, they need to do some calculation practice. Of course they do, but there's more to it than that. Remember we talked about at the beginning about rich and sophisticated problems, varied problems, routine and non-routine. So these are some non-routine activities they can be working on, which at the same time will be developing their fluency. And really nice way to think about multiplying surds is using geometry. And I don't see this very often. I don't see it in books very often at all. So I'm going to share it with you. You may well know, you may well be familiar. Sorry, I slightly distracted. I saw a comment in the chat. Last one is good for a equals 0. Jenny, you mean it's a good one to think about what happens when a equals 0 as well? Yeah, exactly. So b is 0 is a problem. Is a is 0 a problem? And what about a and b being 0? What's happening there? Does that work in any of them? So really thinking about all those options. Thank you, Jenny. That's a really good suggestion. Thank you. And I don't see this idea very often. I don't see it in books very often. So I want to share it with you. If it's really obvious you've seen it before, then just apologies. You can zone out for a few minutes. So here's my triangle. I'm going to make it 1, 1, root 2 triangle. I'm going to make it 1, 1, root 2. But it's a right angle triangle. I should have said that 1, 1, root 2 triangle. And then I'm going to make it 5 times bigger. So I'm going to make it 5, 5. I'm going to make it scale factor, or more accurately, length scale factor 5, and make it 5 times bigger. And so therefore, what's the hypotenuse? Well, by Pythagoras, assuming I'm happy with Pythagoras, the hypotenuse is root 50, because it's 25 plus 25. But the hypotenuse is also root 2 multiplied by 5, because that's the scale factor. If I multiply two sides by 5, I multiply the third side, the length of the third side, by 5. And so it has to be the case that 5 lots of root 2 has to equal root 50. It equals root 50 from the triangle. It equals 5 root 2 from the enlargement, and therefore they've got to be the same. I just think it's a really lovely way of showing those results about surds in an unfamiliar context. So in general, k root 5, well, we can do the same thing. We can start off with our 1, 1 root 5 triangle, and we can enlarge it by a scale factor of k. So we get k, and then we get 5k squared by Pythagoras as being the hypotenuse. But what do I know? I know it's 5 times bigger. No, sorry, I know it's k times bigger. And so k square root of 5 must equal 5k squared. Sorry, I've got the square root. Sorry, it's the square root. So by Pythagoras, it's the square root of 5k squared. And so those must be equal. So k root 5 must equal the square root of 5k squared. And then from that, you can start to see, sorry if I was getting far too many emails. You can start. It's that time of the evening. People start sending emails. Then they can start to see sort of how procedurally you deal with the k outside the root and bring it into the root. But there's just a really nice picture of what is going on here. So I put another one with root 5 in, because one of the nice things about root 5 is you can get it in another way. So what I could do is I could have 3 and 2, and root 5 now is the base of the triangle, or perhaps the adjacent if you chose one of the angles. And so same idea. Let's double the sides. So now it's 4 and 6. And then what's here? Well, it's 36 take away 16 square rooted, so it's 20. So I've got a scale factor of 2. It's root 20 by Pythagoras, but also it's been enlarged by a scale factor of 2. So I have to have that 2 root 5 must equal root 20. So the enlargement tells me it's 2 root 5. The triangle tells me it's root 20 by Pythagoras, and therefore those two have to be the same. And then sort of something like that. Well, we could do it with either of our triangles. We could have either have our well, there's lots of different ways of doing it, aren't there, actually? So not even just either. There's sort of, I can think of certainly 3 ways of doing it. I could do that as 1, 1, root 2, and do a scale factor of root 5. I could think of using a 1, 2, root 5 triangle and think of a scale factor of root 2 and seeing what happens there. But also I could use my other triangle. I could use my 3, 2, root 5 triangle and have my scale factor of root 2. I could use less nice surds. I could have, say, I could have maybe a root 2 and a root 2 and a 2 triangle, and multiply that by a scale factor of root 5. Again, do you remember one of my prompts at the beginning about show me another and another and another and another? You give this one question and you could say find lots of, possibly even all the ways of doing so, of representing it using right angle triangles, and getting to think about the various possibilities. You know, which surd is the scale factor, which surd is the hypotenuse. And then, of course, once we're good at that, then we come on to simplify surds. We can do things like this. Something like that, say. Well, again, can you do it more than one way? So it's 5/6 of 6 root 2. That's okay. But what about taking the 5/6, as it were, into the square root? So what is it? Well, it's 5 lots of root 72 times by 1/36. But also maybe it's just root of 25/36 times by 72. So again, can they do the same thing in more than one way? And then something like the bottom one, what are they going to do? Oops, sorry, what are they going to do with the bottom one? They're going to start multiplying out the brackets. No, stop, always think. What have I got? Oh yeah, I've got 6 root 2, take away 4 root 2. That's what I'm cubing. So it's 2 root 2 cubed. Off I go from there. And it's making sure they're not going into autopilot. Oh, quick! It's a cube. I must do bracket, multiply my bracket. No, take a step back. Can you simplify? Simplify before arithmetic. And then something like this. Okay, so an alternative. You could just make it a practice exercise for simplifying, but then why not make it an ordering exercise? Why not make a comparing exercise? So which of these is bigger, and how do you know which of these is the biggest, which of these is the smallest? How do you know? Well, that's obviously going to be root 200. That's going to be root of 64 times 3, which is 192. This, as we saw a moment ago, can be all sorts of things. Let's think of it as 9/16 times by 320. So that's going to give me root 180. And then what about this one? Well, sorry, my hand keeps bashing the screen low down. What about this one? Well, what is it? It's 1 over root 3 subtract root 2 all cubed. Okay, so let's rationalize the denominator. So it's 1 over root 3 subtract root 2 multiplied by root 3 plus root 2 over root 3 plus root 2 multiplied by 1. Remember, we're multiplying by 1 in the cunning form of root 3 plus root 2 over root 3 plus root 2. And so that gives us, now of course the nice thing about my choice of numbers is that product equals 1. And so I end up with root 3 plus root 2 cubed. Now what's the value of that? Don't know, but I don't need to know the value. I just need to compare it. So what I could say is, well, whatever it is, that's bigger than root 2 plus root 2 cubed. So root 3 plus root 2 is bigger than root 2 plus root 2. And that's 2 root 2 cubed. And then that I can simplify, and then I can compare it with the others. So I suppose I could say that is 2 root 2 cubed, and that would be 16 root 2. And then I can go from there and compare it with the others. So an activity like that is again, because it's an ordering activity, we can then start to use properties of ordering of real numbers, rather than just, we don't need to know their exact values. Jenny's doing M in the chat. I'm intrigued.
Oh, sorry, that was I left my chat open. I'm sorry about that.
I'm just intrigued by it. I wonder when you're going, yes, dubious. And obviously something like that, they're going to get first of all, can they extrapolate? Can they work out what that is? Is that going to be cube root of 12? Is that going to be cube root of 24, of something else? And if so, why? So can they work out what to do in that context? Can they give you a scale factor argument? Can they think about how would a scale factor work for that one, maybe? And then what they're going to end up with, they're going to end up comparing square roots and cube roots. How do you do that? How do you compare the square root of 20 with the cube root of 24, or the square root of 50 with the cube root of 54? Yeah, how do you compare those? Well, obviously some of them you can sort of imagine by size, but in particular, it's not totally obvious whether, say, the cube root of 54 is bigger than the square root of 20. You know, those ones, it's not obvious which one which one. You have to think about sort of their relative magnitude. So I think once they will have the fluency of simplifying surds, but I think there's lots you can do to kind of test, can they apply that? Remember we said about having connected and flexible and accessible fluency. So something like this, you see, this makes sure they've got what they need at their fingertips. Something like this is a really nice way of getting them to be able to justify and hence understand why 5 root 2 is the same as what did I say? 5 root 2 is the same as root 50. Not just know that it is, and then exactly, yeah. So that's what I was thinking. So colleagues just suggested in the chat, what we could do is we could think about sixth roots, or other way around, raise all of them to the power 6. So what we could do is raise all of them to the power 6, and then think about what that gives, how that works. So questions like this, and I've got a sequence of them for you to take away and try out. They're really straightforward, but they've just got that complexity of surd coefficients rather than integer coefficients. So these are just linear equations, but I do things like this all the time. I'm not always amazed because I've got used to it by now, but it's always the case that the students are really flummoxed by the fact that I've got surd coefficients rather than integer coefficients. So if this was 5x take away 6 before, they just go like, oh, obviously x equals 2. In fact it's x root 5. They get really nervous about saying, well, does that mean that x is 10 over root 5? And then they kind of forget what to do when they rationalize the denominator. And then particularly down here, they might get to that stage. And then a lot of them will grind to a halt, because they won't recognize this as being a changing the subject context. So they won't think about like a factor there of x. And so x is 6 over root 5 take away 2, and then I rationalize the denominator and take it from there. Because they're so used to, when they have integers, if they've got 7x take away 3x, they work out that 7 take away 3 is 4. They don't think of it as being x lots of 7 take away 3, which therefore x lots of 4, which is 4. They don't understand that what they are doing is they're momentarily factorizing the common factor of x and then simplifying the expression that is the factor, in this case 7 take away 3. So I think things like this are well worth trying, and ask them what's the same, what's different. Simultaneous equations, so here's some examples I've made up to share with you. So elimination, so multiply the top one by root 2 and bottom by 3, or multiply the bottom by root 2, see what happens. Substitution, that's in a relatively straightforward form deliberately. There's something like that, you see, do it either way. Which one's easier, which do you prefer? It's getting them to reflect on the different methods and come to give you an idea of which would they choose and when and why. And then, of course, you can say, now make up your own. So once they've experienced the complexity of solving equations with surd coefficients, then you say, well, now you've done some practice, now make up your own. Quadratics, okay, formula, done that, completing the square, done that, factorizing, done that. So just make that tiny variation, change from integer coefficients to surd coefficients, and they will scratch their heads, they will stop and think. Some of them will grind to a halt because they have the fluency. They'll look and say the bottom one and go, oh, so penultimate one and go, right, I need two numbers that multiply to make negative 30 and add to make negative 5. And the fluency, you multiply to make that, you add to make that, somewhat falls apart because they then struggle, quite rightly, struggle productively with the fact that they're adding to make negative root 5 and they can't see what that is. Even completing the square, they know what to do, or you take half the coefficient of x. So they'll write that, and then they'll get very uncertain about what to do next, because they won't be thinking about, well, I know what that is. That's half times 2 root 7, and so it's root 7, and then completing it from there. Pun fully intended, completing the square by completing it from there. So I find things like this are really good to give them that fluency with algebra, the practice of algebraic skills, but with some additional complexity so that it's not repetitive practice. And then simply trigonometry. So these questions, they all involve obviously 60s, 45s and 30s, because you want to embed the knowledge that cos 60 is a half, sin 60 is root 3 over 2, tan 30 is root 3. That's the knowledge you want them to have, but you want to put it in a context. So something like this, what do we want for x? So x is the opposite, x is the opposite. So what do we know? We know that so if we sort of think about sine 60, well, I mean, how I always say height times sine 60 is opposite. I always think about trigonometry as being scale factors, internal scale factors. So it's the scale, so the sine scale factor is the scale factor from the hypotenuse to the opposite. The cosine scale factor is the scale factor from the hypotenuse to the adjacent, which that isn't, sorry, slightly embarrassing. That's still the opposite. Oh dear, and I'm recording this. That's the cosine scale factor from the hypotenuse to the adjacent. So similar triangles, you have scale factors between the triangles. Right angle triangles, you have scale factors within the triangle, between the sides of the triangle. And similarly here, the tangent scale factor is the scale factor from the adjacent to the opposite. Adj times tan equals op. So that's how I always think about trigonometry. I think about it as being internal scale factors. Anyway, so that means, therefore, that here, the opposite is going to be 6 times sine 60. And obviously we know that sine 60 is √3/2, and then we can go from there, and then sort of similar things here with tan 30. So you're revising trigonometry and you're revising surds, and then something like that, a little bit more complicated. So let's look at B. Well, what do I got? I've got the opposite of the hypotenuse. So sine of B is √3/12. Okay, what's that? Well, that's √3/12. So that's √1/4. So that's a half. And what does that mean? Oh, that means B is 30. So I think I find that going backwards and manipulating the surds to go backwards is definitely an additional complexity. What have we got here? Well, are these right angled? Not necessarily, and indeed the first one definitely isn't. So now we're going to start using the sine rule, the cosine rule. So question mark squared is 7 squared plus 4√2 squared. Subtract 2 times 7 times 4√2 times cos 45. Make that a bit more like question mark squared, and then work all that out, and fingers crossed, if I've done my numbers correctly, you'll get a nice answer using this. I mean, you can see how it's all going to work. You've got 4√2 times cos 45, and so again, you're practicing like the fluency of using those special values, but with this additional complexity. This they find really hard, is my experience. So sine rule, off we go. We do x over sine 45 is x plus 5 over sine 60, and then a bit of multiplying both sides by, so x sine 60 is x plus 5 sine 45. Even this, putting the brackets in, can be a bit of a stumble. I think, do we need the brackets in? Will you tell me what's missing from there? And then we head up a bit of space, and so we get to x sine 60, and then the idea that this is x sine 45 plus 5 sine 45, that you can expand the brackets, because they're not seeing sine 45 as being a factor, as being a multiplier. They're seeing it as being a trigonometry, a thing. So they don't think you can expand the brackets. And then, of course, we have the same issue we had earlier, which is you put the x terms on both sides. Sorry, you have the x terms on the same side, and then recognizing that once again, we've got a changing the subject situation. We've got ax subtract bx is c. And so what do? We factorize. So it's x lots of sine 60 take away sine 45 is 5 sine 45, etc. from there. And again, that step there is really hard to see, because they want to subtract, because they're used to doing it with numbers, and they don't realize that what they're doing is factorizing. And then just a couple more. This is not my question, it's a lovely question. I nicked this from a former colleague of mine. So you just track it through, and the numbers work out nicely. And similarly there, so how high is the rectangle? And then this is quite a nice thing to end with. literally today end with, but also little lessons, is that they learn sine 30, cos 60, etc. But actually there are exact surds for 15 and 75, and you might want to use this triangle to work out why that's the case. And this is great for kind of non-routine problem solving. You know, actually this might work quite well online collaboratively. You know, put them in groups, give them the triangle, and say, right, you know, work out, tell me everything you can work out in this picture. What size can you work out? What angles can you work out? What lengths can you work out? And how do you know? Are you sure? And then from that they can build up a nice expression for sine 15, and also obviously therefore tan 15 and cos 15 and tan 75 and cos 75 and sine 75, and put it all together, and they'll get some nice surds which are not too complicated, and is a nice sort of extension of the 30s, the 60s, and the 45s. So I'm going to pause there, draw breath there. What I hope I've done today with you is shown you lots of examples, and I'll send these slides to you pretty briskly, that you could then use. You could use some of these exactly, or you could adapt them and use them with your year 11s to really develop what I was thinking about as I put this together. I want to develop their procedural fluency, but not in a repetitive, not in a what I was told I was being trained, not in a drill and kill way, not in a repetitive way, in a way which makes them stop and think, what do I do and why am I doing it? So how do I solve x sine 60 subtract x sine 45? What do I do and why does it work? So that's what I was looking for. I hope at least some of that has hit the spot. I'm going to shut up now, you'll be pleased to hear. Very happy to take questions, very happy to go back to other slides. Also very happy for you to go and disappear and get on with your warming beverages. Bye for now, folks. Thank you.